Okay, good morning again, Professor David J. De Los Reyes. My next topic will be a long video format discussion, and this will now be alternating current circuit, and this is lesson number 13. Okay, we are running smooth on lesson number 13. Okay, let's proceed. Alternating current circuit, lesson number 13. The title of the topic is actually impedance in series, or it seems it's a series circuit. Series circuit, the one in series are the impedance, the total opposition offered to the flow of alternating current are impedance. Okay? Okay, let's try to bring out the figure. The figure we are given an alternating current source with the voltage E and frequency, and connected in series with it will be Z1, Z2, and Z3. It depends on how many impedances that are connected in series. But for this illustration, we are given 3 impedances in series. Okay, let's try to bring out the formulas for impedances in series, or impedance in series. Considering for the meantime true impedances, the formulas that will be needed here are actually these two. The foundation of series impedances are these two formulas here. That is, for a series impedance, the voltage of the source should be equal to voltage across Z1 plus the voltage across Z2 plus the voltage across Z3. We add them vectorially. Okay, they are complex numbers. The voltages are complex numbers. It got real parts and imaginary parts. So this is actually formula number 1. No matter what happens in this world, for a series impedance, the total applied voltage will be equal to the summation of the voltages V1, V2, V3. It depends on how many impedance that is connected in series. Okay? That's formula number 1. Okay? Let's try to compute why the impedance in a series circuit is the summation. Okay, it was derived from this. We rewrite the given equation E equal to B1 plus B2 plus B3. Then we will try to multiply the given equation by the ratio 1 over I. The circulating current here is I. It is common, meaning the current passing through Z1, Z2, and Z3 are the same. So we got a total current I without any subscript, meaning to say the current is common. Okay? So if we try to multiply the given equation by 1 over I, what will come out? Left hand side will become E over I. Right hand side will be B1 over I plus B2 over I plus B3 over I. We distribute the multiplier 1 over I, right? Okay, but take note, the ratio voltage over current is actually impedance. If under DC circuit, voltage is equal to IR, that's for DC circuit. For AC circuit, voltage is equal to total current times impedance. This is for DC, this is for AC. So by using this relation here, we will remove this one, we put it here. Okay, so the ratio voltage over current is actually impedance. So I place it here. Since voltage over current is impedance, okay, what will come out? The total applied voltage divided by the total current will be the total impedance. This is capital letter C with the subscript total, the capital letter T, meaning total impedance, equal to the voltage V1 over current I is actually Z1. It is the impedance number 1. And the ratio of voltage 2 over current I will be Z2, impedance number 2. And the ratio of the voltage across this divided by the current is actually C3. So the next formula for a series impedance or series circuit, the total impedance will be equal to the summation of Z1, Z2 plus C3 plus uh, up to how many things, okay? But for this example, only up to 3 impedances, so this ends up to Z3. I will repeat it. The total impedance of a series circuit will be the summation of the individual impedances, that is C1 plus C2 plus C3, but the operation should be vectorially, okay? Use your knowledge of complex numbers, okay? So that complex numbers from algebra, it got an importance here on AC circuit. The operation here should be vectorially. You add them by using the so-called real part and imaginary part, okay? Just combine the real parts, just combine the imaginary part, and that's it. You change to polar form or rectangular form, that's it. Okay, I will try to give you an example problem for impedance in series, okay? Series connected impedances, okay, this one. I'm referring to this problem to this figure here. I will put the value of Z1 to be 3 plus G4. This is plus, so this is an inductive load. I will put C2 to be equal to 4 minus G6, this is minus, so this is a capacitive load. C3, it is 6 plus G9, this is plus, so it is still an inductive load. Could it be that this is a motor load, and this is a motor load, and this is a synchronous motor, which is overexcited to act like a capacitor, okay? So these are the 3 impedances expressed in rectangular form. So the unit is omega. This is ohms, 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 okay? And luckily, this given example, all the impedances are in rectangular form, okay? So it's an easy thing for us to add. Okay, let's try to bring up. No, the applied voltage will be 120 volts, angle 0 degree volts. It says we are on USA, Okay, USA. The household voltage coming from the utility line here in the USA is 120 volts. There are 240 volts, but those are for other applications. But 90% or 80%, it is 120 volts. Okay? The requirement of the problem is fine. Okay? Z total, the total current, okay? The total true power, capital letter P with the subscript T, total true power, S with the subscript T meaning total apparent power, capital letter Q with the subscript T again, so this is total reactive power, and lastly, the problem is asking for the power factor. Okay, let's try to bring out the solution. Using the first equation here, second equation, Z1 will be, or why Z1? Sorry for this one, it's not C1, this is C total. We are getting old, right? We are computing for the total impedance. So the subscript should be capital letter T, meaning total. Total impedance will be capital letter Z with the subscript capital letter T, we equal to Z1 plus Z2 plus C3. Z1 is 3 plus G4 plus 4 minus G6 plus 6 plus G9. Okay, then try to combine similar terms. Okay, this is now algebra, right? Try to group those that are with the same, what you call this, classification. So real part, real part, real part. So this is open quantity 3 plus 4 plus 6 closed quantity. Imaginary part, we factor out the common factor J. Open quantity, this is 4, this is minus 6, and this is plus 9 closed quantity. This is preceded by the G side, meaning this part here is a part of the imaginary part. So this will become 13. 4 minus 6 will be minus 2. plus 9, that will be plus 7. So the total impedance in terms of rectangular form will be 13 plus G7, symbol for omega meaning ohms. Okay, let's try to convert this impedance to polar form, because in the computation of the current, what we need is not only the real part, it is not the imaginary part, it should be the combination of 13 plus G7, and which we will add it vectorially. It seems we are considering a right triangle for the meantime that the real part is 13, the imaginary part is 7. So in the computation of the current, it should be the hypotenuse. So we must have to convert this 13 plus G7 to polar form. Okay? Just take the ratio 7 divided by 13, press arctangent. Okay, what will come out will be 28.3 degrees. Okay? The angle should be less than 45 degrees because the ratio 7 over 13 is actually less than 1. Because the tangent of 45 is actually 1. 7 over 13 is not 1, it's just only around half, point something. So it is 28.3 degrees. Take the cosine of this. Okay. Divide that cosine value to the value 13. What will come out will be 14.76. Or take the sine of this. You divide that sine value from the value 7, and that will still be 14.76. That is now by using your calculator. Or the third solution, if you want the Pythagoras principle, it will be the square root 13 plus the square root 9. You add it, then take the square root. What will come out should be 14.76. Angle 28.3 degrees ohms. This is a positive angle. Okay. So meaning to say, it is overall inductive. So we are expecting a lagging power factor, meaning the motor loads actually come out, right? So because this is 28.3 and this is plus G7, it is an inductive load that comes out. Okay, let's try to compute for the current. The total current will be the total applied voltage over the total impedance. Okay, I will now express the total voltage to be 120 angle 0 degree. Why 0 degree? We always use this as the reference vector under AC circuit, the applied voltage. Whatever the magnitude, we put the angle to be 0 degrees because we use this as our reference vector. Okay, so it will be 120 over angle 0 degree over the total impedance. Take the magnitude on the polar form, not the real part or the imaginary part. It should be this 14.76. So this should be 14.76 angle 28.3 degrees. Performing the polar division, the magnitude will be the ratio 120 over 14.76, which is 8.30 degrees. And the resulting angle of the current, 0 minus 28.3, this is minus 28.3 degrees. So this negative sign here means lagging current. Okay, it is this. This is the applied voltage, and the current lags this applied voltage by an angle 28.3 degrees. It is downward. So this negative sign here means a lagging current. Okay. How about the total true power? If we try to compute for the total true power, we use absolute values here. We don't have to use the polar equivalence. Or just take the square of the current times the resistance. The current magnitude is 8.13, right? And what is R? R is this 13 here. That is the real part of the impedance. Okay? So this is times 13. What comes out is 859.26 watts. Actually, this is the one we are paying to the utility line. If you try to multiply this by hour, what will come out will be watt hour or kilowatt hour. Kilowatt hour. That's the one we are paying to the utility line. If you try to multiply this 859 by how many hours you use in a day, that will be your total energy consumed. And the utility companies will charge you for that one. Okay? S total will be the product, total apparent is total applied voltage times total current. Just compute for the absolute value. The total applied voltage magnitude is 120. The total current is 8.13. What comes out for the total apparent power? The capital letters S with subscript T, meaning total apparent power will be 975.6 volt ampere. Okay? If this is to be multiplied by 1000, you will see the rating kVA, or the figure 1 will be MVA. Okay? So if you try to notice the rating of the transformers hanging on the post, it is in terms of kVA. MVA, it's not in the post. This is million volt ampere. This should be the rating of substations maybe. But for distribution transformer on the post, the rating is in terms of kVA. VA is very small. It should be kVA. Okay? How about the reactive power of the inductive load? Capital letter Q with the subscript capital letter T, meaning total reactive power. It will be the square of the current times X of L. Okay? This portion here is the motor load. So the total consumption of that one will be 8.13 quantity square times 7. This should be 462.67 reactive volt ampere. Reactive meaning the imaginary part component, the motor load component, bars. So if this is to be multiplied by 1000, you notice that the rating will be in kilobars. Right? The figure 1 will be megabars. Okay? And these are the rating for, what they call this, motor loads. If it is plus, it should be motor loads. If it's minus, it's a capacitor or a synchronous motor that is overexcited to act like capacitor. Or how about the power factor? Power factor, one definition of power factor will be the ratio of true power over apparent power times 100%. We now know true power, we now know apparent power. Take the ratio, 859 divided by 975.6 times 100%, and this is 88%. With the condition, they should be lagging. That's a lagging power factor because this is an X of M, right? It's motor loads. Okay, if you want to, where's my calculator? To check this 88%, one of the definition of power factor is that it will be the cosine of the angle between the voltage and current. And the angle between the voltage and total current is 28.3. So if you get your calculator over here, 28.3, this should be in degrees. Take the cosine of this. This is multiplied by 100. And this should be 88%. Same as this one. Okay? So this just checks the correctness of this power factor to be 88% using the ratio true power over apparent power. Or as a second solution, take the cosine of the angle between the applied voltage and current, and that will still be power factor with the given condition, lagging. Okay, that's it guys. So for those of you who are taking up electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJ.De I am discussing concepts and example problems under my long video format, so you will learn something from the long video format discussion. Okay, good morning from Los Angeles, Professor David J. De